Well, hey there, everybody. I'm Chili. I don't know why I decided to use that voice, but anyways, this is the Hitler's Uranus Gravy Surfer. Yes, that is the name of the project. And today we're going to be talking about multi-threading acceleration. It's going to be fucking sweet. We're going to take all those goddamn lazy cores that have been sitting around collecting unemployment insurance with their fingers up their butts, and we're going to make them productive members of society. So the first thing that we want to figure out is what are we going to multi-threadalize? Because we've got 4 passes here, and I'm going to be damned if I'm going to do them all. That's fucking too hard. I'm going to do one because it's going to show you guys the kind of gains that you get from multi-threading and the actual process of multi-threading. But I'm not going to do them all because it's just the same thing 4 times. Waste your time, more importantly, waste my time. So I benchmarked all 4 of these passes to see which one was the bottleneck or the biggest detriment to our performance, and I found out that by far, my wife, it is the Upsize pass. So here's the results from the Upsize pass run 32-bit build. And it's about 1.12 milliseconds. The rest of them were all around 0.3 milliseconds, 0.25, 0.3. So this is like over 3 times slower than any of the other passes. So it's definitely going to be our target of choice. I just took all of these benchmarks while I wasn't recording because that's a little more accurate. Benchmarks taken during recording are a little less accurate, especially when you use all 4 cores. But anyways, so yeah, our target is going to be the Upsize blend pass. Now, it's not going to be like, the hardest part of this is going to be dividing up the problem into different jobs for the different threads. The actual multi-threading part itself, not that complicated in general. And that's the case for any kind of problem that falls under the class of embarrassingly parallel. Embarrassingly, I don't think I spelled that right. That's embarrassingly. Parallel, that's probably right. This one, not so much. But anyways, yeah, you call these kind of problems embarrassingly parallel. I'm not sure why it's embarrassing. It's not like, people saw your dick. Not that I'd be embarrassed if people saw my dick, because I have no shame. But in general, what embarrassingly parallel means is, well, for example, in our case, any line of processing we have here, for example, downsizing from here to a line into here, doesn't depend on any of the other results of the other parts of the processing. All these processing are all independent of each other. They also write to completely mutually exclusive areas of memory, so they don't have to synchronize with each other in any way. And that means that they're really nice to implement in multi-threading. So our job is going to be pretty easy. But, like I said, the hardest part for this is going to be dividing up the job. Because right now, as it stands, well, let's take a look here. Upsize blend pass SSE. Oh, let's go collapse the definitions first. Let's see if that helped. Didn't help. Nope. It doesn't work on the lambda functions. But as you can see here, here's where we calculate all the pointers and everything. And this is doing the job of the Upsize blend pass. Let's take a look at that here. Nope, that's not it. This is the one. Nope. Yes. Okay. So what the Upsize blend pass does, if you're not up on your Chili Bloom processor, is it basically does whatchamacallit, bilinear filtering to upsize by 4 in every direction. So 4 times the width, 4 times the height, 4 times the girth. Now the problem with the Upsize blend is it's kind of asymmetrical. It's got some edge cases. So the top and bottom lines, they generate the top 2 and the bottom 2 lines of the result. And then every pair of lines in the source generates 4 lines in the destination. So every pair, 4. So what that means is, first of all, you've got these 2 special cases at the top and the bottom, and 3. Did I say 2? Because I meant 1. Anyways, 3. You have of the pairs that you have to process to get these 4-line results, you have 191 of them, which does not divide nicely into, for example, 4, which would be the number of threads we'd want for my processor, which has 4 cores. So the job does not divide up nicely. And also, it's just a bunch of pointer bullshit, and it's a pain in the ass. But you can do it. It's not that hard. And I'm not going to go into the details of how I divided the job up into. It's not that useful information, especially since those details change every time you're going to want to implement multithreading. Depends on the job, right? So we're just going to gloss over that. You can look at the code if you're really interested in how I divided that up and calculated all the pointers. And if you have any questions about, how I divided that shit up, you can ask me in the comments or on the forum. So let's get down to it. So how does Chili do this? Well, first off, I create a class to represent my worker threads. So every thread is going to be an object of class Upsize worker. So let's look at the data that this class has. It has a thread object, so it holds on to the thread, which is different than the previous case, where we just created a temporary thread object and then detached it immediately. Here we are not detaching, we're keeping the thread, and I'll show you how that works a little later. We've got a condition variable and a mutex, and they work together. Well, the mutex protects these 2 flags here that the main thread is going to signal to the worker thread. The started flag and the dying flag, and the CV worker is going to be obviously used for the main thread to signal the worker to start doing its job. All right. So, where to start? I guess we could start off in the constructor here. Now, there are 3 types of workers. Basically, every worker, we're going to divide no, not this. Didn't want to put that up there. We're going to divide up the job of upsizing the buffer into 4 sections, like this. So the top and the bottom sections, they're also going to have to deal with the special cases on the top and the bottom. These special cases here and here. So, and they're also going to have to do, the normal cases here, upsizing from 2 to 4 lines. The middle cases here, they don't have any specials. They just do the middle lines and that's it. So that's why I have 3 different types of workers. The top worker does the top section. The bottom worker does the bottom section, and the middle workers do the 2 middle sections. So how they calculate their pointers and how the actual job is performed depends partly on the type. All right, so we've got the upsize worker. It takes a bunch of pointers to the input buffers, or the input buffer, the output buffer, some dimensions like the pitch of the input buffer and the width of the input buffer, and the pitch of the output buffer, the type of the job, and a reference to the boss, which is the Bloom processor here, and that's going to basically represent the main thread. And we do the same thing that we did in the MIDI shit. We lock, and then we create the thread. This time we're not creating it temporarily, we're assigning it to the thread worker member of Upsize worker. And we capture all of these variables here to be used within the thread itself. And here we lock, so we prevent the thread from continuing on until, oh shit, we gotta get rid of this shit here. This shit's gotta go. Where is it? This is necessary. Upsize edge. That's not necessary. This is not necessary. So this is actually just exactly copy and pasted from the original SSE3 code. I didn't change anything. I just copy and pasted all these lambdas into here. And that's why I say it's super easy to do the multi-threading, because you're just basically copy and pasting most of your working code from your single-threaded stuff. And then just dividing that job into 4 jobs. So scan down here. We'll talk about this later. So here we finished creating the thread, that's this. And then the main worker is going to wait until the thread has finished initializing. So initialization of the thread. Well, first thing is I gotta talk about is the capture here, because this was actually really tricky and it fucked me up for a little while. Because the first thing I tried was, okay, I'll just capture them all by value. You can do that with just a single equal sign. That'll capture all of the local scoped variables by value. And that's easy and it makes my life easy, but it doesn't work. And the reason why is if you try to capture a reference by value, it's going to try to make a copy of the referenced object. And we don't want to copy the Bloom processor. We don't want to make a second Bloom processor. First of all, because the Bloom processor copy constructor is deleted. And second of all, because it makes no goddamn sense. So then I said, okay, well, I'll just capture them all by reference. And that was a terrible idea, because think about it. This constructor, it's going to start the thread. The thread is going to capture references to all of these parameters. But the thread keeps running even after this constructor leaves, or the execution exits the constructor. And when the execution exits the constructor, all these variables get destroyed. So now your thread has captured by reference a bunch of variables that no longer exist, and that is a bad time. So you actually have to type all this bullshit out. You capture everything by reference, including this pointer, except for the boss, which you wait, did I say reference? I meant capture all these by value, and capture only the boss pointer by reference, the pointer to the Bloom processor. All right, so now we have our bullshit captured. What are we gonna do? Well, we're gonna lock. We're gonna wait until the main thread is waiting for us to finish initialization. So once the main thread enters its wait on condition variable, we are free to proceed. And this is just all the initialization that we did in the beginning of the normal single-threaded thing, where we just basically create all our Lambda functions. This probably doesn't generate any code except for this part up here. It's basically just declaring the functions that we're going to use within this function. Within this thread lambda, I guess. Lambdas within lambdas. I do like my lambdas, but anyways. So all this stuff is exactly the same as before, no need to explain. Here is where we declare all of the pointers that we're going to be using for our processing. So these are the pointers, well here, you've got the pointers for the special case for the top edge or bottom edge, depending on what type of job we are. And the pointers for the middle line sections that we're going to be looping through. And then you initialize those parameters based on what kind of job you have. So it's a top or a bottom job, you're going to initialize the edge parameters and the middle parameters. And if it's a middle job, you only have to initialize the middle parameters. And these parameters are used, well, especially the start ones, are used to start every pass of the thread, or every pass of the job thread, right? Every frame, because every frame you're going to start from the same position and then work your way down to the bottom of the job. All right, and once we've done initializing all that bullshit, then we notify the main thread that we're done initialization, and we do a little bit more initialization here. Here we're just we're taking those start values and we're putting them into the pointers that are going to get incremented as we work our way down the job buffer area. So we do a little bit more initialization here. And then we set started to false, which is the signal to the main thread that we're done initialization. And then we wait on the condition variable, which releases the mutex, which allows the main thread to continue. And the condition for waking up here is either the started flag has been set or the dying flag has been set. And then the main thread is going to call, it's going to set one of these flags with a, with a command. And we're going to wake up because the condition variable is going to be notified. And then the first thing we're going to do is we're going to check if we're dying. And if we are dying, we're going to break out of this infinite loop. And breaking out of the infinite loop just, what does it do? It just leaves, I guess this is the infinite loop right here, I believe. Let me check. I can't tell. Yep, so it'll just leave the thread, exit the thread, kill the thread. So this dying flag just kills the thread. Fairly simple. Makes sense. If we're not dying, then we must have gotten a started message because that's the only other condition that can make us wake up. So then we check our type. If we're to type top, we do an upsize edge for the top. Then we do all of our middle ones where we call the do line lambda and then increment our pointers by the, the proper amount. And we keep doing that until we hit the end point. Then we check to see if we are a bottom, because if we are, we've got to do upsize edge for the bottom stuff. And then we notify the boss that we're done, which is basically we lock a mutex on the boss. The boss has its own mutex. That's down here. So I added to the Bloom processor, added the condition variable and a mutex for the boss, the Bloom processor. And also just an integer here for the number of active threads. So what we do is when we're done, we decrement the number of active threads under the mutex, and then we notify the boss. And that is how the boss knows when all the threads have finished working and it can continue. But that's the whole thing. That's the whole worker thread right here. Most of the bullshit that I had to figure out and debug was in calculating these goddamn pointer values based on, the input pointers that specify the region that this worker is doing. So the worker gets a region that it is in charge of, and it is in charge of that region for the entirety of the program. It always works in that one region. And yeah, that was the most complicated part of that. So that is that's the thread, the worker thread itself, the thread procedure, if you will. I deleted some stuff that we're not using, and here are the functions that the main thread calls. Very simple. It's the same stuff as the MIDI. You lock the mutex, set the flag, and notify. Here is the little different, because here we're not using condition variables to wait for the death of the upsize worker. We call threadWorker.join, and when you call join on a thread object, it waits until that thread object has exited. So again, we lock the mutex, we set the dying flag, we notify, and then we join this thread, and that will just allow us to wait without having to wait on a condition variable or anything. It's the same thing as with the MIDI, it's just a little simpler. So that's what you can do if you maintain the thread object. Where is it? In here. Then you can call join on that object later on and wait for its death. If you call detach, then you can't join it because it's no longer joinable. So yeah, that is basically the whole goddamn upsize worker object in a nutshell. Now beyond that, like I said, you've got in the motherfucking where is it? The motherfucking Bloom processor. You've got condition variable for the boss, a mutex for the boss, and active threads for the boss. So what those are for, and you've got a vector of unique pointers to upsize worker. Now, I made the vector a vector of unique pointers instead of a vector of just plain upsize workers, because upsize worker is not movable or copyable. So, and if an object is not movable or copyable, you can't use it in a vector, because vectors have to be able to move shit when you resize the vector, right? When the vector grows and it gets reallocated, it has to move those objects or copy those objects. And you can't copy or move an upsize worker because you can't copy or move a condition variable or a mutex. So instead of doing a whole bunch of bullshit to make them copyable, I just said, fuck it. I'll just wrap it up in a, where the fuck is it? Wrap it up in a unique pointer, and then my life is way easier. And I use that solution all the time. Unique pointer is your friend. Vector of unique pointers, very nice. Also polymorphic. Okay. So anyways, this shit is also used in the Upsize blend pass SSE3 multi-threading function. And this one just, this is basically to call the start of the thread, to start the thread working and wait for all the threads to be done. So again, you lock the mutex of the boss, and then you set the number of active threads equal to the number of threads in the vector of workers. And so that would generally be 4 in my case. So I set the number of active threads to 4, then I tell all the workers to start, and then I wait on the condition that the number of active threads has gone back down to 0, meaning all the threads have finished. And that's the other side of the coin. Where is it? Fuck you. The coin here, where we lock the boss mutex and we decrement the number of active threads. It's the other side of that coin. All right, so that's basically all the multi-threading stuff here. Up in the constructor of the Bloom processor, I add a call to function init upsize workers, which creates the actual workers. And that function is here. It's a private function. And it just does basically the thread calculations that we had before, only divides the space up into 4 spaces. So every thread does, well, the first 3 threads are going to do 48 middle lines, and the last thread is going to do 47 because it doesn't divide evenly. And as you notice, the first one, the type is upsize worker top, then you've got a middle, and you got a bottom. So we basically just push these workers, unique pointers to the workers, into the vector, initializing it with the proper pointers. And it's a kind of a pain in the ass to do all this calculation, especially since we have those fringe regions which aren't actually shown on the screen, and so you have to take them into calculation. It's a pain in the ass, but you can do it. And that's about it. I can't think of anything else that is really important here to talk about. That's everything I did. And when you do this, let's build it. It has already been built. And you run it. Let's see here. Stop that. Let's see what I'm interested to see how this compares to the measurements that I took without the camera on, the screen capture, that is. So yeah, 3.1, 3.3, 3.2. It's pretty close to what I got before. What I got before was, let's see here, multi-bench up multi-thread MT 32-bit. So here's 32-bit multi-threading. So yeah, about 3.1. Yeah, it's a little slower when I got my camera software running, but same thing. So yeah, about 300 microseconds compared to single thread 32, compared to 1,125 microseconds. Much, much faster. And just so that you know, if you set this motherfucker up for 64-bit multi-threading, you get 27, so 270 microseconds, and 64-bit with AVX enabled, so you get the VEX instruction encoding. You go all the way down to about 240 microseconds. So that is like over 4 times faster, but that also takes into account, using 64-bit instead of 32-bit and so forth. But in general, just comparing apples to apples, 32-bit single threading and multi-threading, I could get about a 3.7 times faster, which is pretty good. especially considering that the theoretical maximum is going to be 4 times faster, right? Because you got 4 threads. And you're not going to get the theoretical maximum because even though you quadrupled the amount of threads, and even though there is no synchronization between them, you've not quadrupled the memory bandwidth. And so those threads are still sharing the same memory or the same cache. And so you're going to get what you call diminishing returns. So you don't quite get 4 times performance with 4 times the cores, but we get pretty close. About 92% of optimal efficiency. That is not too bad. It's nothing to shake your dick at. So, yeah. Now there's one more thing I want to show you. Because when I first started playing around with multi-threading, I didn't do it right. So what I did was, I did basically the same thing. I divide the job up into 4 sections, but I launched 4 different threads for the 4 sections, and then I joined those threads every single frame. So every frame I was creating 4 threads and then joining them, and it works fine if you do it like this. And I figured, it's a small function call compared to the processing. It's not going to take that long. Actually, it does take that long. Let me just run this here. So these threads aren't doing anything. They're just being created and then immediately being, exiting, and then we join. So how long does it take to create 4 threads that do nothing? It should be in here. Wait, that can't be right. I don't trust that. Let me check. What is the name of this here? T-log. Okay, that's a little better. T-log. Where is that? Here it is. So yeah, about 300. This is a little slower, I think, because I'm running my camera software, but about 300 microseconds. It's pretty good for creating 4 threads. So it actually takes a sizable amount of time for the operating system to create those threads and get them running. And so that is why you don't want to create separate threads every single frame. Unless you have a very large job, like your job in single thread takes maybe, I don't know, like over 30 milliseconds or something. Then you're probably not, it's not too bad to just spawn the threads and do the job and then join them. But in general, if you're, for example, if we were to use this method with the, because there's a 300 microsecond overhead, if we were to use this method with our whatchamacallit here, with our multi-threading system here in the Upsize, we'd be over twice as slow. So by creating the threads once and then communicating between the main thread and your worker threads on the fly, keeping those worker threads working and communicating via condition variables, you're gaining over 200% speed increase in this case. So that is why this shit is necessary. Otherwise, I wouldn't do all this bullshit. I would just spawn a thread, do the job, and then, join the thread. All right. Now, the last thing I want to talk about is in general, like in our case right here, it is, as I said, an embarrassingly parallel problem. And it's also nice in that we can divide the problem up into 4 equal jobs or almost equal jobs. And why is there a line here? That's weird. Anyways, so we can divide that up into 4 equal jobs, give those to 4 different threads, and the threads will do those jobs finished at the same time. Everything's nice. It's very simple. But in general, see, the way that the reason why these jobs are all basically equal is because there's no branching, right? Our algorithm is completely branchless. So independent of the data, it's always going to take the same amount of time. But in general, you're not going to have a situation like that. Most algorithms, they have some branching, and they have some situations where even if you can divide the work up into an equal number of work items, this work item here might take like 10 time units, whereas this one might end up taking 40 time units. And so if you do it like this, the whole job is going to take 40 time units, right? And that's bad because in 30 of those time units, these threads here are just going to be sitting with the thumbs up their ass waiting for this thread to finish. So it's not, in general, it's not a good idea to just divide up your job into n pieces where n is the number of threads and just dole it out in big chunks. What you want to do is you want to divide your job up into lots of tiny pieces. And what that does is so let's say thread A, B, C, and D here, they're going to work on these individual pieces, and they're not going to sit around when they're finished, when they're finished one big section and, do nothing. What they're going to do is we're going to take up some of these other jobs here. And that means that instead of the job finishing in 40 time units, it's going to finish in 70, basically 70 divided by 4, which is 35 divided by 2. It's going to be like 17.5 maybe. So instead of taking 30 time units, it's going to take 17.5 time units, almost twice as fast. So in general, you want more granularity. You want fine grain jobs. And then you're going to have a queue. That's a G. That's not a Q, that's a G. You're going to have a queue, Q-U-E-U-E, of jobs. And every thread is going to take jobs out of the queue when it has finished the previous job. And when the queue is empty, then you're done. And this is a little more complicated because now the threads are kind of interacting with each other a little bit, but only a little bit. They're not interacting a lot. So job queue isn't a big deal. And you can even make lockless job queues that don't require a mutex. But that's all outside of the scope of what I want to do here. Just some food for thought. So in general, unless you can guarantee that all your jobs are going to take the same amount of time every time, you want to be using a fine-grained job granularity, and you want to be using a queue of jobs. But that's it for today, I guess. That has done it. Multi-threading acceleration. We did it over 3.5 times faster. Very nice. And one more thing for those of you still watching. I'm currently working on a new series, well, actually a reboot of the original beginner series, and another series which is going to be teaching 3D concepts, how to render in 3D. And I'm developing stuff for that. I'm making things like a new icon, logo, bullshit. I want to make an intro. And I just wanted to know if any of you guys watching, if you have any experience in, producing video intros and stuff like that, any tips you can give me, or you can get into contact. I would be interested in hearing your advice, because I've never done this before. I'm shit at that. I'm probably going to have to, fire up Blender or 3D Studio Max or something and fuck around in that. But anyways, if any of you guys have any insight for me, I'd be happy to hear anything you want to tell me. And if you like the video, click the like button. It's cool. It makes me happy. And you can, leave a comment. Tell me how great a guy I am. That'd be cool too. And I will see you when I see you again with something else. Maybe from HUGS. Maybe from something else, or maybe I'll see you in a live stream, but I will see you.